Good afternoon, everyone. Thank you for joining Panel 2, Session 4, the final session of Panel 2, where we will be talking today about technology development. I have a few housekeeping items before we jump into the talks. So first off, I want to thank all of the sponsors for making this event possible, especially DTE, the host sponsor. Please click on the sponsor link on the left-hand column of your page to visit their sites and learn more about their work. We have an exciting lineup of speakers this afternoon, and after all the presentations are given, join us for the last 15 minutes of the session as speakers answer a few questions from the chat. ACEEE will collect any remaining questions unanswered that go unanswered and send them to the speakers to respond after the conference. With this in mind, you can see the chat box on the right-hand side of your screen. Please use this box only to ask questions for the speakers and refrain from engaging in dialogue with other attendees. If you would like to connect with other attendees, please take advantage of the attendee link also found on the left-hand column of your page. Any attendee who has created a profile can be found there. In the column, you will find attendee resources as well, and the resources contain conference proceedings, attendee list, and an evaluation survey that should be completed at the end of the conference. Anyone who fills it out and includes their name and testimonial will get a discount to attend the 2023 summer study. In the program participants link, you'll find information about all of the presenters, including bios and copies of their presentations. And lastly, please join us at the end of the day, shortly after this session actually, for the post-panel debrief to learn about other discussions that you may have missed. Remember, all sessions will be recorded and available on demand after the conference. So let's get started. Our first speaker is, actually the presentation is going to be co-presented between Ed Ryder and Paul Shine. Ed is the director of the industrial program at ACEEE, where amongst other roles, he develops and leads the strategic vision for the industrial sector. Prior to joining ACEEE, he had several leadership roles at Dow during his 31-year career. So I'll turn it over to Ed now, and he'll introduce Paul.
Okay, well, thanks, Kate. I'd like to acknowledge my co-authors on this paper, including Andrew Hoffmeister, Neil Elliott, Paul Shine, who I'll introduce briefly because he's going to co-present with me. We've also had the benefit of collaborating with folks at NREL and Oak Ridge, Travis Lauder, Jordan Cox, Scott Belding at NREL, Kyle Glusenkamp, Bo Shine, and Kashif Nawaz at Oak Ridge. Let me give the introduction for Paul. He'll speak after I get a few of the slides going here. He's the principal at 50,001 Strategies, a company which assists manufacturers and commercial companies to create and deploy strategies which integrate strategic energy management within business plans within the ISO 50001 management standard. He's also supporting ACEEE on this industrial heat pump work. Paul spent 30 years with the U.S. Department of Energy. It's a AMO manufacturing office, partnering with U.S. industry on energy efficiency, and he led DOE's Superior Energy Performance Program. Earlier, he had led DOE's Industrial Heat Pump Program. So with that intro, let me just go on here and acknowledge also sponsors of this project, including NYSERDA, Bonneville Power, Southern Company, and Tennessee Valley Authority, and of course, I already mentioned our partners on this project. So you might ask the question, why industrial heat pumps now? Industrial heat pumps have been around for quite some time. Why focus on them now? Two principal reasons. One is science-based targets, as we've heard during other sessions during this summer study, are encouraging companies to make aggressive goals for greenhouse gas reductions. With those goals set, then the question becomes, well, how are they going to meet those goals? One of the pathways or pillars for reduction, which we talked about yesterday, was electrification, where the electricity comes from low carbon sources. And heat pumps are one of the principal means by which the industry can deal with the process heat through electric means. There also have been technology advancements in several different areas, working fluids, compressor innovations, and also the advent of heat-activated heat pumps. Additionally, there are other benefits in addition to just energy benefits. Of course, greenhouse gas reductions is part of the story here, but there also are aspects of improved control, speed of response, and others that industrial heat pumps can provide that help to bolster the justification case for heat pumps. I just want to point out to this slide that was presented earlier this week that you may not have seen, or you may have seen it, and I'll just reinforce it. So industry accounts for a large portion of the greenhouse gas emissions in the US at more than 25% across several different sectors. And across all those sectors, a common feature is that process heat accounts for a large portion of that energy usage. Not only does the heat account for a good portion of the energy usage, but the heat varies depending on its temperature range, perhaps also its pressure range. But let me talk about the temperature range in particular because it's important to the application space for industrial heat pumps. On the left-hand side of this figure, you can see that for chemicals, refining in the food sectors, the relative thickness of the blue bar, if I point it out here, is relatively large. And what this shows is that there's a significant opportunity in chemicals, refining, and food for applications that can provide process heat in the moderate temperature range. That's just where we want to talk about industrial heat pumps because they certainly today can get up to 80 degrees, but as Paul will talk about, they can also get to higher temperature ranges, especially with the advent of new working fluids. And it can be applied in a number of different application areas. You can see the process heat hits not only fluid heating, such as distillation, but also drying, several other applications, as well as you can see on the right-hand side, industrial applications where several of these industrial heat pumps could be applicable. So let's talk about key areas for this research, looking at three key areas. One is the market fit for not only current and emerging industrial heat pump technologies, but also those on the advanced end as well. We want to understand the fit of those technical capabilities with the market needs, and we also want to think about policy enablers that will help drive adoption. For this, the parties on this collaboration have different elements of the story that they're providing. ECEEE, and Paul will tell a little bit more about this, is we're scouting top processes. We're doing analyses of pinch curves to understand the best application of the heat pumps as well as the economics. And we want to understand the energy and greenhouse gas impact and to see where efficiency opportunities that can help to drive the application. The National Renewable Energy Lab is looking at techno-economics as well as process heat analysis. And our collaborators at Oak Ridge are looking at modeling, testing, and standards development where they have capabilities. The key part of this research is really to revitalize industrial heat pump research in the US because it has languished in the last few years. Certainly those in Europe and Japan and other locations, Australia, have really advanced industrial heat pump research. We want to leverage what we can, collaborate with them where we can as well, and bring it home to the US. I'll mention sources of heat as well as sinks, just as an introduction to what Paul is going to talk about here, and to note that there are several different kinds of sources with different temperature ranges, which are the light blue circles in this figure, the bottom part. And the challenge here with industrial heat pumps, or the opportunity, is to take the heat and to upgrade it, if you will, to the temperature ranges and the applications, potentially in the light brown areas, bubbles up on the upper right, upper part of this figure. That's going to be the role of the heat pump. So at this point, let me pass it over to Paul.
Thanks, thanks, Ed. Okay, so there's a phenomenal amount of opportunity here with industrial heat pumping, as Ed has mentioned. Heat pumps have been used in U.S. industry to some extent, and many times they're not even called industrial heat pumps. You see the chart of what I would classify as 5 different types that we're going to investigate. The type of heat pump we're probably most familiar with would be the closed cycle mechanical vapor compression, which is analogous to the heat pump that we might have on our house or commercial building. But there are other types of heat pumps that have been used. For example, the open or semi-open cycle systems called mechanical vapor recompression, or MVR, or thermal vapor recompression, TVR. These are used quite extensively. Well, I should say they are used in, for example, pulp mills, food plants, chemical plants. And these types of heat pumps are very interesting in that for what we call low lift application, you could simply recompress steam or recompress a hydrocarbon and recapture that energy with only a small amount of energy from the heat pump. But even more interesting, I think, are the heat activated or absorption heat pumps. You don't see too many of these in application, definitely not in the United States. And they could be either type 1 or type 2, and I'll explain those in a second. So let's go to the next slide. So this is a very basic diagram of a mechanical vapor compression heat pump, and where we have an evaporator where we're taking the heat in from the heat source, and we have a heat sink where we're putting heat into some type of stream to heat the fluid alternatively from process heating. And then you have an expansion valve to expand the working fluid into the evaporator. And then we have to put work back into the fluid with a compressor. Most times the compressor is driven by an electric motor. Doesn't need to be. It could be driven by a heat engine. Or in the case we'll get into with the absorption systems, the engine is a pump, liquid pump. So let's go to the next slide. Okay, so this shows how we might think about heat pumping a little differently with a heat-activated heat pump. But it's the same, we're trying to accomplish the same purpose of moving heat up. So we have the useful temperature of the heat that we're trying to serve. We might, in the type 1 heat pump on the left, we would use a hotter heat source to drive the absorption heat pump. And then we pump the heat up from the source temperature. Typically, these type 1 absorption heat pumps have a coefficient of performance of 1.6. That means for every 1 unit of heat I'm delivering, for every 1.6 units of heat I am delivering, I only need 1 unit of heat to drive it. The type 2 heat pumps I love these because they are mostly entirely waste heat driven. They need a little bit of electricity for pumping of the liquid, but they would have a COP of 0.5. That means I need 2 units of waste heat for every 1 unit of heat I pump up. I do need a driving force between the source temperature and the ambient to be sufficient enough to lift the heat up. So these, if we look at advanced cycles in the future, these were the kind of things we want to look at, these heat-activated heat pumps. Next, please. Okay, so let's think about what we're really trying to do with the heat pump in an industrial process. Well, we're trying to replace out the conventional way of heating a fluid, which is usually steam, boiler steam, or perhaps a direct fire process heater. Of course, we're burning fuel on the right-hand side with some level of combustion efficiency, and that heat is coming out of the boiler with steam or the process heater and heating the process. But alternatively, with a heat pump, where that condenser we showed before, that is what's heating the process stream. And we do have to put in some heat pump driver energy. So we need to keep this in mind, because the more we lift the heat, the greater the lift of temperature, the more work we need to put into the heat pump. And we'll talk about that in a second in terms of the economics. So the economics are going to be driven. Why don't you go back one? Just finish that up. The economics are the lift temperature, the cost of the heat we're saving, and the cost of the heat pump driver energy. All that's going to, those three factors are going to drive the economics. Okay, next. All right, so as Ed mentioned, looking at the process systematically, and we're using pinch point analysis, we have the benefit of hundreds, over 100 processes where we have pinch data. And we are starting to investigate these processes for heat pump potential. So pinch analysis has been around for almost 40 years. And in every process, you have heat sources or that are being cooled on the left, and we have heat sinks that are being heated. And if we look at how to match the heat sources, the heat sinks to each other, or what's called hot and cold streams, there's a point where the pinch point, where above the pinch point, there's a deficit of heat that you have to add in heat. And below the pinch point, you have excess heat where you have to remove heat. So you can do what's called heat integration to better match the heat sources and heat sinks to save energy with adding greater heat exchange. And also you can put a heat pump in. But what you want to make sure with heat pumping is you want to pump from below the pinch to above the pinch. Okay, let's go to the next slide. So what we did, we looked at about 4 processes, and I'm going to show you one. This is for ethylene. And so you can see that pinch point, which is about, I think it's about 350 degrees Kelvin, or about 80-something degrees, 85 degrees Celsius, which is a little bit under the boiling point of steam, right? So here we have the hot streams and the cold streams. If you click one more, Ed. Here we go. We found one opportunity where there's waste heat from the quench stream, quench water, and we can then heat. The heat sink will be a distillation tower where the reboiler is going to be heated by the heat pump. And the cool thing about this is the lift to do that, you can see from the heat source to the heat sink is less than, I think, around 15 degrees Celsius. So that's what you want to find. You want to pump around the pinch, and you want to find a lift that's as small as possible to minimize that driver energy. We also found that with this particular application, we could use a semi-open cycle mechanical vapor recompression. What's the advantage of that? Well, you'll need one less heat exchanger. You can take the hydrocarbon directly and pump that up to heat the incoming reboiler requirements. Okay, let's go to the next slide. Oh, yeah, here's a summary. So we can save 12% here. That's pretty significant, right? And with a coefficient of performance of 10.7. That means I only need about 10% of the electrical energy to get 10 units, for 10 units of heat provided by the heat pump, I only need 1 unit of electrical energy inputted into the heat pump. All right, so you get a little over a 3-year payback. So this is, of course, ethylene is a huge chemical feedstock or building block, if you will, in the chemical industry. A tremendous amount of energy used to make ethylene. And we found a temperature for the heat pump that's fairly moderate at 85 Celsius. This is definitely, could be serviced by existing heat pump technology. It was a low lift application, less than 20 degrees. That's the key. And we were able to use that semi-open MVR, which gives good economics. You want to look for an attractive or low electricity to gas price. I'm saying usually less than 4 is a good opportunity. And then maybe we'd have other opportunities with the advanced heat activated systems above 50 degrees C. Okay, let's go next slide. Keep moving along here. So our colleagues at NREL have done some case studies and modeling for the dairy industry. And this is a big energy consumer in the food processing industry. And they found a number of possible applications to heat with the heat pump: milk pasteurization, homogenization, and ultra pasteurization. You go to the next slide. These bubble charts show the results for one type of heat pump, a closed cycle mechanical vapor compression system. And they did it for different states that had attractive electricity to natural gas price ratios. And they even did it for certain county levels within states. And so the blue bubbles show a net positive return on investment. And the red showed not so good with a break-even. Now, that is not to say that heat pumps are not attractive in California or Texas. That's just saying for this particular type of heat pump, for this particular current situation with the electricity and natural gas price today, maybe not so good. But the blue would show they are good. So the idea is we're getting started on, modeling heat pump opportunities in the United States. Okay, let's go to the next slide. I love this slide because it really shows a list of the key applications you want to look at: drying, evaporation, etc., and where we are with heat pump technology in the world. And what's amazing is our collaboration with our European and Japanese partners, for example. It almost seems like week by week we see a breakthrough with heat pump technology. This is such a hot area, and there's so much going on in Europe, and there's been a lot of research dollars put into a research consortium there that this chart is changing regularly. And for example, we saw last week the Norwegians came out with a heat pump that they feel is commercially available at 180 degrees C. Compressing steam, for example. Phenomenal opportunity, and the range of opportunities going to continue to increase with heat pumping. Okay, next one. So this, I think, is my last slide, right, Ed?
Yes.
Okay, good. And so this shows the 4 applications we have done so far. I already showed you the ethylene. And I think the key takeaways are there are opportunities, and you can kind of see the amount of lift we're looking at, the waste heat versus the heat sink. And we're saving anywhere from 8 to 26%, and some fairly significant heat pump sizes up to 7 megawatts. And you can see the number of facilities in the United States that could potentially be impacted. And we just did 4 processes, and probably, over, looks like 200 or so processes with fairly good payback with very low natural gas prices currently, $3 a million. If that gas price changes, if it goes up, that payback's just going to go down. And okay, so I'm going to switch it back to Ed.
Okay, well, thanks, Paul, for illustrating the current state of the project. We've got a ways to go at this point, but we've certainly scratched the surface of a pretty big opportunity. You had mentioned the price ratio between electricity and natural gas. And I just wanted to point out that that varies depending on where you are in the country. Location matters. And the folks at NREL had showed us that it matters not only at the state level, but also potentially at the county level as well. And you want to be in the lower end of that ratio for applications, but just because of the fact that you're in a somewhat higher range, just may mean that you need to think of different choices relative to the type of industrial heat pump, as Paul mentioned. So in this space, I noted the drivers relative to decarbonization, science-based targets, and others that are coming in, driving the sustainability of corporations. Out of that, we need, for accelerated adoption, coherent, predictable policy framework to help really accelerate that type of adoption. That's going to lead and be in parallel with needs in several different areas. We've listed 4 here. There's going to be technology interests and needs. And part of our research here is to increase that awareness and to get information in people's hands to help engineers make decisions on deciding what kind of industrial heat pumps might be most applicable. There also needs to be field support. It's not the kind of industrial heat pump that you would buy in your house, where you just call up a couple of vendors, get a couple of quotes, they come and install it, and life is good. Industrial heat pumps are a lot more complicated, and they're tailor-made in many applications, and they're integrated to specific needs of applications. For that, there's going to be needs for field support, engineering support as well. There also is need for collaboration, not only for the type of collaboration that we've started here on understanding the applicability of industrial heat pumps at the starting gate, but also what we term clearinghouses for data, so that people can understand where they can pick up parameters to see what industrial heat pumps would work in best applications. And eventually, for some demonstrations, there might be discussions needed on intellectual property and potential for sharing intellectual property. Policy is going to play a role here, we believe, as well, certainly to help broaden the applicability. One of the opportunities is to help defray the electricity cost in certain areas of the country, which have moved the needle relative to electricity to gas cost. Support for demonstrations, particularly at scale, for some of the industrial heat pumps that Paul mentioned, like the heat-activated heat pumps, for example. Clusters of industrial companies, such as the Houston Ship Channel area up in Chicago, where there's a lot of steel, out in various ports, like the Port of Los Angeles. Those clusters could be demonstration centers for large industrial heat pumps. And we think that there's also need for support of what we call a middle tier. That's the field level support, where companies would go and not only provide the support for front-end engineering design, but also support once the heat pumps are installed. And that kind of brings me to the summary, where we wanted to just point out that we're at the early stage of this research, but what we found so far from the screening economics is that we want to minimize the lift, the temperature lift, going for the smallest lift where possible. We want to minimize the number of heat exchangers needed. So that's where the application for the mechanical, the MVR came in that Paul mentioned. And we want to look for applications where that price difference between electricity and gas is low as possible. But again, there's other factors that need to be considered. Want to also look for opportunities to apply the advanced capabilities, not only for the working fluids, but also some of the advanced applications such as the heat activated systems that Paul had mentioned. So what we've seen so far is that the applications we've examined in these case studies show a good potential from an economic perspective for industrial heat pump applications at scale and larger scales. And I'll note that there are several demonstrations, particularly in Europe, in refineries and others that are pushing the scale. The next steps is to scan additional processes, to verify the estimates that we've got, the parameters we've been using with industrial partners, and to, again, further look for the fit between what the market needs and the capabilities for not only the current emerging, but also the transformative industrial heat pump technologies that are coming down the path. And we will also want to provide input for policy enablers and to help policymakers understand the potential impact if there were to be policy instruments in the space to accelerate adoption. So there, of course, we're looking for greenhouse gas impact, jobs impact, and others. So let me stop there and I'll hand it back to Kate.
All right, thanks Ed and Paul for a great talk. This is just a reminder to please, I see a couple questions in the chat, just please feel free to add questions to the chat as the talk is going on, and then we'll capture those in the Q&A session at the end of this session. So next up, we'll be hearing from Tina Marie Karsberg from the Advanced Manufacturing Office in the Office of Energy Efficiency and Renewable Energy at the U.S. Department of Energy, one of my coworkers. There she manages a portfolio that includes nanotechnology, semiconductor, additive manufacturing, metallurgy, and thermal energy products. And she leads the Cable Big Idea Prize team. She's trained in physics and has had, prior to AMO, had an extensive career at first in academia and then in the Department of Energy and in government for the last 20 years. So please join me in welcoming Tina, and she will introduce her co-presenter as well. Thanks, Tina.
Thanks, Kate. Good afternoon, everyone, and thank you, ACEEE, for hosting this conference and including our paper. I'd like to also thank my two co-authors, Shashank Misra of Sandia National Laboratories and Kenta Shimizu of Energetics Incorporated. Here, I and leader Shashank will summarize the key points of our paper and provide additional context based on events that have occurred since we completed it, including at this very conference. Shashank, who is the principal investigator of the Transistor Project, will provide details on overcoming manufacturing challenges to make this extremely energy efficient transistor. Shashank started as technical staff at Sandia National Laboratories in 2013, and he now leads their effort in developing the science and technology of atomic precision advanced manufacturing, or APAM. For AMO, he's trying to use APAM to make energy efficient transistors. All right. But first, a really quick overview of AMO. Since this is the last session on the last day, I'm betting you've seen some of this information before, but did you know that AMO has been involved in energy efficiency for the information communications technology sector for at least 10 years? Second, I want to introduce a major new driver for AMO's efforts in semiconductors, the Biden administration's climate goals: zero carbon grid by 2035, 50% reduction in carbon emissions by 2030, and the overall goal of net zero carbon economy by 2050. These goals all increase the urgency of deploying decarbonization technologies, such as extreme energy efficiency, massive electrification, and increased digitalization, meaning increasing use of semiconductors. From our first day in office, our secretary has emphasized.
Sorry, you just need to share your slides again.
I need to share them again? You can't see them?
Yeah, I don't have them up. Nope. Just share them again and I'll have them.
Okay. Sorry about that, guys. Yeah, I knew something would go wrong. Alrighty. Yeah, I can't see the. There, can you see them now?
Looks good. Good work.
Okay, just flip backwards really quick. Okay, this is our front slide and the 3 co-authors. This is the AMO office. This is showing the Biden administration goals that I was just talking about. And next are our AMO goals. In the past, AMO has focused on reducing the energy intensity of manufacturers themselves, and that is still a top goal, including for semiconductors and manufacturing. But AMO now has a mandate to partner with manufacturers to make things that are more energy and resource efficient over their life cycle, or goal 2. And then in April, AMO announced its new goal, a decarbonization goal, and this is where we believe that foundational technologies such as ultra energy efficient transistors, coupled with smart digital manufacturing and that leverage industrial electrification, can have the biggest impact. And of course, in making this impact, it's vital that we also meet the goals relating to circular economy, rapid technology transition, and strengthening the US workforce. In this next section, I'll briefly describe how transistors function to discuss their foundational role in microelectronics, literally at the bottom of the stack. One trend I will discuss is the end of automatic Moore's law energy efficiency increases, and another industry trend is the larger focus on energy improvements higher on the stack. So how do transistors work? When the voltage is larger than the threshold voltage for that transistor is applied to this gate here, you can see, the current appears on the drain side of the transistor over here. And the above threshold voltage provides a conducting path between the source and the drain. Remember these terms for later when Shashank describes his new transistor. The fact that the silicon from which a traditional transistor is made is conducting some of the time and other times is not, is why it's called a semiconductor. The transistor is a switch where the higher on voltage represents a 1 and the lower off voltage represents a 0 in binary logic. Most of the commands in digital computing and the data stored are made from strings of 1s and 0s. And then over here on the right, this is why we put transistors down at the bottom, because they're really foundational, fundamental building block of all computing and microelectronic applications. So many of you have heard of this Moore's law, but it's not really a law. It's more like a microelectronics industry roadmap goal. The line on this log chart shows the fit of the actual data on how many transistors are on a chip. And the Moore's law is basically that the number of transistors on a chip doubles every 2 years. And this is an amazing pace of miniaturization that lasted from the 70s until the 2010s, when, as Shashank will describe, the shrinking of the conventional metal oxide semiconductor transistor began to reach its limits. So, but why do we care about transistors shrinking? The reason we care is the smaller the transistor is, the shorter the distance between the source and the drain, and the lower the input voltage needs to be. And the lower the voltage, the less energy the transistor uses. And the energy is related to voltage quadratically, which is why, as Shashank will describe, a new transistor that uses 1/3 the threshold voltage is an order of magnitude more energy efficient. Oops, I went the wrong way. Because we have this multi-trillion-dollar infrastructure devoted to making this particular type of transistor, the semiconductor industry has found it easier to achieve performance improvements higher in the stack, even as transistors reach their geometrical and thermal limits of how many could be packed together. So, for example, there's been a rise in popularity of application-specific chip designs for artificial intelligence applications with the graphical processing units, which are much faster than general processing units or CPUs. But meanwhile, back at the research lab, new transistor technologies, such as those shown here on the right, still continue to be developed. But none of these promising transistor concepts has been de-risked enough for widespread adoption, which is why AMO sponsored a workshop this April on manufacturing processes and tools for ultra energy efficient devices to identify the manufacturing research needed to commercialize these next generation transistors. A better transistor is foundational because general purpose computing communications will continue to expand exponentially. So as noted, microelectronics have done a great job of keeping themselves very energy efficient as their performance improves, and until recently. But more importantly, microelectronics are key to enabling the rest of the economy to become more energy efficient and decarbonize in two ways. First, with extreme energy efficiency, ACEEE studies have shown we can get halfway to zero carbon with just efficiency improvements, everything from smart manufacturing, sensors and controls, energy demand reduction. Microelectronics can help. Second, to get the rest of the way to zero carbon, as mentioned by our Assistant Secretary, we need to decarbonize industry as well as all of the other sectors. And one key strategy is electrification and high-performing, low-cost, next-generation microelectronics will be key to making electrification more affordable and near-term strategy. So how exactly do microelectronics accelerate decarbonization? Well, they lower costs and improve performance of things like, the energy management system approaches that we've been hearing about that are the first step in decarbonizing and energy efficiency with low initial costs and low operating costs microelectronics. Second, the next step is upgrading capital equipment and installing new, more energy efficient electrical technologies, like those great industrial heat pumps you heard about. Those will also benefit from lower cost, lower initial and operating cost microelectronics. And finally, we talk about adding renewables, and that is really challenging, with integrating electrical and or thermal storage, and also will require electronics. Finally, we had a sensors workshop, which is the first in our series of workshops, and concluded that to really get the full promise of energy efficiency and electrification, we need to develop and deploy integrated sensor systems as ubiquitous wireless systems with edge computing. So this slide is intended to show some of the urgency in getting these new energy efficient microelectronics out. We hear all the time from climate scientists about why we need emissions reductions now, or we have 10 more years left is what we hear all often. But there is another reason for urgency, even without considering climate impact. At our workshop in April, 5 speakers showed some version of this chart showing how semiconductor energy use, after decades of being fairly negligible, has started to increase exponentially and could become a significant fraction of planetary energy use in the next decade. This trend is not surprising given the confluence of end of Moore's law efficiency increases and the rapid digitalization of our modern economy, especially post-pandemic. Even absent a climate crisis, we cannot economically afford to let semiconductor energy use become a significant fraction of planetary energy use. SRC's phrase, the market dynamics limit, is really a euphemism for world market collapse in 2035. And we can't afford for semiconductors to become part of the climate problem rather than the solution, which is why our motto for our AMO microelectronics program is 2030 or bust. And just to quickly summarize, extreme efficiency, energy efficiency technologies that use the order of magnitude less energy can help halve emissions, and it's even possible to do that in a decade. Okay. So it turns out there's at least one microelectronics technology that is at least an order of magnitude more energy efficient than those used today. The one we're highlighting, which was voted as the tunnel field effect transistor, was voted as the most promising logic device for energy efficiency in our recent workshop. And now to explain why this technology is so energy efficient and describe its manufacturing challenges, I would like to turn it over to my co-author, Dr. Shashank Misra. Shashank, are you ready?
Yeah, thanks, Tina. So if we could go on to the next slide, slide 14. So to understand why tunnel field effect transistors, or TFETs, are more energy efficient than MOSFETs, which are the state of the art, I'm going to resort to an analogy with water buckets. Okay. So on the left-hand side of this slide, what we're going to try to do is we're going to try to pick up a bucket and transfer the water into the other bucket. And when we start doing that, as we tip the bucket to get the water to flow out, the bucket's going to start sloshing, okay? And so when it starts sloshing, you'll have a gradual increase in the amount of water that's being transferred from one bucket to another. And so that, conceptually at least, is how a MOSFET works when you gradually get more flow as the bucket starts to tip over, okay? So the way to think about a tunnel field effect transistor, which is a candidate next generation transistor, is that it's more like having two buckets that have a valve connecting them, right? So you suddenly toggle on the valve and the water just begins to flow, okay? So in this analogy, I think an important thing is that either the action on that valve or that tipping of the bucket, that horizontal axis of both of these graphs, that's how much energy you're putting in order to get that switch to work, right? Tina said earlier that transistors are effectively switches. That vertical axis is how much work you're getting out. All right, if we could move to slide number 15. All right, so like Tina noted earlier, transistors aren't buckets of water, but they actually work with voltage and current. And here, the horizontal axis is voltage, and that voltage is how much energy you're putting in, and the vertical axis is how much work you're getting out, okay? So you'd like, if we want to take a look at the MOSFET, the thing that's happening here is that you would like to have a little change in voltage give you a big change in current. And so it's the slope of that line, that 60 millivolts per decade, that's what's determining how energy efficient that transistor is. So the advantage with TFETs is literally that that initial slope of that line is very steep. And that's because they use a fundamentally different mechanism, a different physical principle to turn on. Next slide, please. So that's how TFETs work, at least in theory. So that low subthreshold slope again means that you've got a steep line and you can just run that transistor at a lower voltage than you can compared to a MOSFET, the transistor that's in wide use today. Again, like Tina said, a factor of 3 decrease in that voltage is a factor of 10 improvement in energy efficiency, and that's what's been predicted. In practice, you have the spaghetti that's sort of on the right-hand side of this slide, and there are a couple of notable problems, but I want you to focus on two of those curves really. So that black line, that dashed black line, that's the current to voltage relationship for state-of-the-art MOSFET. So the blue line that's below it, that blue line is an efficient TFET, and you can see that the initial slope of that line is very steep. It's steeper than the black line, but it actually ends up saturating out at a current on the vertical axis that's much below the black line, and that lower level means that transistor is effectively it can do less work, right? Like it's just not going to run as fast of a speed as a traditional MOSFET, and that's a problem. So conversely, we could focus on the red line, and the red line, we're actually getting to that current level that the MOSFETs can get to, and that means that transistor is going to be just as fast. But the problem is that initial slope isn't any steeper, and so you can't run it at any lower of a voltage. So in practice, TFETs have practically been stuck between these two extremes, where you can have them be efficient and slow, which is no good, or you can have them be reasonably fast but inefficient, which means that they don't really have the advantage. Next slide. So the next little part of my talk, I'm going to indicate how manufacturing could overcome those two problems with the TFET. Next slide. So So what goes wrong with a TFET that you don't get enough current? So what's limiting that saturation current? So understand that we actually have to slice a transistor in half. And so what I'm showing you here is a cross section of a MOSFET and a TFET. And so this is the second time you're seeing this, so I'm hoping it's a little bit more comfortable than the first time. And in a MOSFET, the source and the drain are two pools of electrons. And when you change the voltage on the gate, what happens is that the electrons from one side, from the source, they flood across to the drain. So that's kind of like having a fast one-lane highway is what the gate's turning on between the source and the drain. So for a TFET, the TFET actually works a little bit differently. So there you have a complementary kind of carrier to electrons. Those are called holes. Semiconductors are unique in the sense that you can easily manipulate both kinds of those carriers. And in a tunnel field effect transistor or TFET, what's happening is that that gate is pulling the holes close enough to the electrons that they can kind of jump across the barrier. But you can't ever get rid of that barrier, right? And so that barrier actually, it's responsible for the efficiency, but at the same time, it's going to limit that current. So it's like having a speed bump on your one-lane highway, right? It's just always going to be a limit. Next slide, please. And so the cute or the insightful solution we had to this was, instead of having a TFET that's working horizontally, like that cross section shows, where you have the drain, there's that single black and white arrow connecting it over the source. We thought, what about making it really vertical? Okay, so in the TFET that's drawn on the right, what's happening, instead of going right to left, you're actually going vertically when the gate turns on. And so now you've got many lanes of traffic. Now they each still have a speed bump, right? But now you have many lanes of traffic in order to get the same amount of current that you would with a MOSFET. So that is, if you could make that device on the right, you'd have a chance of overcoming the current density problem. Next slide. So for the limitation on the energy efficiency is actually also related, and to manufacturing, I mean. And here, this has to do with what happens as the holes get close to the electrons. And you can just think about it as, what does it look like when the green region, the blue region get close to one another? So in a perfect world, everything's exactly how you made it. The way you drew it up in some drawing programs is exactly what happened when you got the transistor out of the silicon foundry. And in that case, that perfectness is what that subthreshold slope being so steep, that's what that's based on. And that 20 millivolts per decade is actually a quantum mechanical limitation based on the size of the wave function. So in practice, actually what's happening is that the actual reality of the manufacturing limits how sharp those blue and green regions are. And really for the blue region, what's happening is it's getting smeared out badly. When it gets smeared out badly, you're no longer limited by nature, but you're limited by your manufacturing technique. And that's why that efficiency isn't what it's sort of theorized to be, but it's been less than ideal. And ideally, we'd be able to define the source, we'd be able to define those dopants that constitute the source and the drain, we'd be able to define them with atomic precision. Next slide, please. And so that's actually what this project is about. It's about using atomic precision advanced manufacturing to be able to make that device. And atomic precision advanced manufacturing, or APAM, what that lets you do is it lets you define the source and the drain. It lets you define them with atomic precision. Okay, and that's not to say that they're a single atom large. That's just to say that the boundaries of where you want the dopants to be, that they're exactly where you want them to be, and they're not where you don't want them to be, right? And down to the single atom scale. So the way APAM works, you can think about that as being a manufacturing technique that's very much like how silicon is grown. So that silicon's typically grown as a film on a substrate, and the APAM process, what it does is it dopes that silicon using using chemistry, using surface chemistry. Now, APAM got its name because that growth process can be atomically precise in the growth direction, but APAM can actually also template it in plane. You can have that stretch from being something that is really fast and manufacturable on one end, or it can be pretty slow, but you can also define it atomically in plane, right? So you can have things down to the single atom scale, but that's not terribly manufacturable. It turns out that the TFET that we've chosen to make, that lateral length scale isn't terribly important, but that vertical one is, and as a consequence of that, you have the control that you would need in order to be able to realize a TFET that has that extreme energy efficiency. So what I'm showing on the right-hand side there very quickly is what the manufacturing workflow would be. I think here, rather than talk about each step, step by step, because we're going to run out of time, instead what I'd like to say is, that process, in this process, APAM fits in the middle of the actual manufacturing workflow. And so to get that process, which hasn't been commercialized yet, in order to figure out how to fit it in a manufacturing workflow, you have to make sure that APAM isn't disturbing anything that happened to the silicon before it. And you also have to make sure that none of the subsequent steps in the manufacturing workflow disturb the APAM, right? Like, so for example, if any subsequent step applied a lot of heat, what's going to happen to that doped layer is that it's going to smear out, right? The APAM is putting in a density of dopants that exceeds the solid solubility limit. So if you add heat, it's just going to kind of dissolve into the silicon that surrounds it. Next slide. So here, the point that I want to make is that we have a project with Tina, with the Advanced Manufacturing Office. The project is called Big Energy Efficient Transistors, or BEATS, because I like interesting contractions. And the point of the project is to take APAM as it exists now, where it's really a technology that's used to make demonstration devices, so to demonstrate basic physical principles, and to increase that manufacturing complexity that surrounds it in order to actually build up a transistor, right? So to get not just a source and drain contact, which is how typical devices are made, but to be able to actually get the gate involved and get that vertical structure built up. The last thing here, I think this is really important. Look, this is a small research project at a national lab. It's not like I'm Intel, and just as important is to build up the understanding of the modeling framework to understand these devices, because what you'd like to be able to do is project how good this transistor would be if it was adopted by a big silicon foundry. Next slide, please. So accordingly, we've actually thought a lot about what it would take to do a manufacturing handoff. Again, this is something that's existed at the lab scale for its history. And so as part of a separate project, actually, Sandy has done quite a lot of work in trying to figure out how to make the process manufacturable. And there are two aspects of that. One is that you have to actually understand semiconductor manufacturing. Sandy is fortunate in the sense that it has a silicon fab that makes custom ASICs for the government. And so we've been able to insert APAM into the middle of a CMOS manufacturing workflow. And we've also been able to show that there are ways of making that process really manufacturable at scale. And here, I think the most exciting development recently is that we've been engaged with a tool manufacturer on a nearer term application. This actually has to do with contact resistance in MOSFET. So in the same transistor that's in your cell phone, it turns out they think that APAM can make that current technology better, and that would be a way of getting the tools that would be needed to make a TFET in the game. And I think with that, I'm actually handing this back to Tina to wrap up.
All right. Thanks, Shashank. This chart shows the considerations of which transistors, some of those other transistors I showed you early on, and how they rank according to their energy use here on the vertical, and how they rank according to their time. So there's some debate about how important speed is. But as you can see, this sort of desirable area of very low extreme energy efficiency transistors is dominated by TFETs, but there are other types of transistors, and we also are researching other types of transistors at AMO.
And Tina, if you could just wrap up.
Yeah, this is my last slide.
Okay, great, thanks.
So what Shashank told you about TFET commercialization path is actually true for an entire suite of atomic precision process and the other transistor concepts, because we have this huge structure. We have fabrication facilities that make the chips now cost tens of billions of dollars to build one of these facilities. And companies like Intel do not want to take risks trying a whole new different device in this fab. They require thousands of steps, and so many things could go wrong. And so an Intel or some other fab would never license Shashank's TFET technology directly, but they might purchase new process capabilities from companies such as Applied Materials that Shashank is working with, or Novellus, Varian. There are a whole host of tool makers, and that's what this chart is supposed to display. It's just you never would have a new device startup that would make a transistor and license it to a device maker. That just would not happen. There's just too many risks. The way you would get a new manufacturing technology for a device into circulation is you would do what Shashank is doing and take pieces of it and try to solve near-term problems with existing technologies for the tool makers. And in that way, various parts of the process can get to the tool makers, who then use these tools with devices. And that's sort of the indirect way that we're looking at for trying to commercialize these devices. And in so doing that, eventually the likelihood that we'll get this new transistor will increase. And we're trying to do this in a really accelerated way. That's all we had to say. That's our story of why we need the APAM TFET and what its path to commercialization could be. The fact that we have this virtual conference really helps make the point that it's not just computing where we use a lot of microelectronics. So communications applications are growing exponentially. So thank you for your attention, and Shashank and I will be happy to answer questions at the end of the whole panel. Thanks. So I stop sharing?
Yeah, thanks, Tina and Shashank. Okay, so in the interest of time, I'm going to keep the discussion moving quickly, but yes, please add your questions. Just a reminder to add questions to the chat as the presentations are rolling. Our final speaker today is Chris Wagner. He is an engineer at Go Sustainable Energy, where he conducts industrial and commercial energy audits and performs utility measurements and verification, as well as acting as a team member on commissioning projects. So I'm going to turn it over to Chris.
Thanks, Kate. I just want to confirm really quick with those backstage that you can see my slides and hear my audio coming through okay? Awesome, thank you. All right, so hello, everyone. Thank you for attending my presentation today. So the paper that we wrote was on how much focus should be going towards optimizing inherently inefficient compressed air systems versus phasing them out. As a good engineer, I'm going to take a page from the back of the book, and we're going to start with some spoilers. If at the end of this presentation, this is the only slide that you take away, then I'll be happy with that. And it kind of summarizes, you will see this slide again at the end of the presentation, but we wanted to start with the end in mind here. We're currently on what we're calling path 1 right here, which is focusing on energy efficiency with our compressed air systems. We'll go through the numbers, but ultimately what this paper proposes is a second path, which is phasing out compressed air as a whole because it's inherently inefficient. Again, we'll hit these numbers, but the main conclusion here is if we were able to do an energy optimization audit at every single compressed air, industrial compressed air system in the United States, then the theoretical savings match what would be a 20% implementation of phasing compressed air out. So either, we have two paths here. Either we have to go visit every single industrial compressor, or we have to visit about 20% of them. So we'll get into how we arrived at that conclusion. So really quickly, what we'll be going through today is I'll give you a quick introduction to the authors of the paper, what the goals of the paper were. Then we'll be getting into calculations. We'll see graphs, get kind of nerdy while we're calculating the savings of phasing out compressed air versus optimizing it. We'll then kind of talk about sort of the implications of what a compressorless manufacturing industry could look like. And then we'll go ahead and conclude and follow up with the questions and answer. All right, so who are we? So Go Sustainable Energy is an energy efficiency and sustainable energy consulting firm. We deliver accurate, unbiased information on energy efficiency and sustainable energy to our clients. I'm the lead author on this paper, and the two co-authors are Peter Kleinhens and Ryan Schuessler. And kind of the main experience that we bring to the table with this is with our audit work. We've been in a bunch of different manufacturing facilities, and we've had the opportunity to see many compressed air systems with our audit and measurement verification work. So that's kind of given us the experience to bring to this topic. So the goals of the paper. You may have seen this graph a couple times throughout this conference, but the graph on the right is showing our atmospheric carbon. The blue line, which I've highlighted here, is what climate scientists say we need to get down to in order to avoid catastrophic climate change. So for the United States industrial manufacturing sector, we're kind of saying we need to do our homework and do what we can to get the atmospheric CO2 levels down to that level. So let's frame this up for compressed air. Ultimately, compressed air systems, they use about 10% of the total US industrial electricity usage. So the main point here is compressed air uses a lot of electricity. The second point is that fully optimized compressed air systems really only get about 9% mechanical energy output. So not only do they use a lot of energy, but they're also inherently inefficient. And currently have a lot of resources going into compressed air efficiency programs. As just a quick kind of case point example is here in Ohio. We work with several energy efficiency programs, and one of the programs we work the most with, 18% of their custom rebate budget went to compressed air efficiency audits. So, maybe there's a bit of a disconnect there that you can see right off the bat. If we're only using 10% of industrial electricity usage, but 20% of the budget is going to compressed air, maybe there's a slight disconnect there. So really the purpose of this paper is to ask the question and maybe push back on the status quo. Is this the best use of our resources? We think that considering taking compressed air out of the equation could be another potential good use of these resources. So let's go ahead and get nerdy and look at some of the data. We're going to go through the calculations, our methodology, and 4 steps. First, we're going to get baseline electricity usage for industrial US compressed air, so what we're paying for. Next, we're going to convert that electricity usage into useful work, so what we're actually getting out of what we're paying for. Third, we're going to do proposed electricity usage, as if we phased out compressed air and came up with alternative technologies. So this is what we could be paying for. And finally, we'll look at the savings by taking the difference between the baseline and the proposed. So to get our baseline electricity, we took a fairly simple approach. This is the equation that we'll be using to see what the baseline energy is. We're going to take total industrial sector electricity usage, and we're going to multiply that total electricity usage as multiply it by compressed air as a percentage of the total usage. We'll see what some of that data looks like. I know that this graph is small. The intent's not to be able to read each individual piece here, but this is the Manufacturing Energy Consumption Survey, or MEX. This is 2018 data, and it takes the total electric purchases by industry subgroup and reports them. So if we want our baseline for the entire nation, then the simple solution is to sum all of these up, and that shows what total US industrial sector uses for electricity on an annual basis. So then our second source of information here is we're going to look at compressed air as a percentage of the total usage. This comes from the compressed air market assessment. And again, it is broken out by industry subgroup, but the total at the bottom here is 10%. So we will see how those numbers kind of pan out as a whole. So we did multiply the individual pieces here. So if you want to go look at the paper after the presentation, then feel free to see how each subgroup kind of works. But at the end, when we sum total annual electricity usage and multiply it by that 10% value, this is what we're left with. We're left with about 77,800 gigawatt hours per year that the US industrial sector is currently using on compressed air alone. Taking in the climate context for that, this is equivalent to about 35 million tons of CO2 equivalent per year. All right, so step one is done. And now we're going to calculate how much useful work we get out of what we're paying for with these numbers here. So the rule of thumb is generally you're going to lose about 80% of your air compressor energy to the heat of compression. There's a couple other losses that are figured in most common air compressor systems. This is actually some data that was put together by the CEA Technologies in a report for the Canadian Department of Natural Resources. Some of these other losses are, in desiccant drying, filtration and leaks, pneumatic to mechanical conversions. Every compressed air system is going to have some element of these things, and they might, maybe there's less desiccant dryer losses in some and more in others. This is just there to act as kind of a general baseline. And to simplify things a little bit, all that we're looking at here is, the useful output is just this 9 horsepower that remains in this 100 horsepower bar. So the useful output is 9% efficient, and our losses summed up are 91% efficient. So if we compare that to our baseline, this is the number that we calculated in step one, 77,800 gigawatt hours per year. If we multiply that by our useful output percentage of 9%, that results in about 7,000 gigawatt hours per year in actual useful work that can come out of these compressed air systems. So let's go ahead and compare that to our proposed usage. What I've done is I've stacked our proposed usage in a bar down here. You can see we use 70% efficient as our new useful output efficiency. We'll get into that in a little bit. But if it's 70% efficient, that means 30% are losses. You can just see the scale of if this total summation of this bar is what we're currently paying for just to get this little black portion out. It would be obviously ideal to maybe move more to a system that looks like this, where we're losing only a small portion of the energy that we're paying for with the same useful output. So how did we get there? What we took a look at, and we'll go into when we move to our third section, we'll kind of talk about some of the implications here, but we're looking at direct motor replacements as kind of the catch-all here to compare one to the other. And this is the results of ASHRAE. This was published in ASHRAE Journal in a 2004 article. It's showing by motor size what the full load efficiency will be for several different types of motors. The industry best practice right now is these EC motors, electrically commutated motors. And at their least efficient, which is the smallest range, they're sitting around 70%. What we kind of see in some of these older, we see a lot of permanent split capacitors, and up to about 1/2 horsepower, they're now coming up to the 70% range. So in order to remain conservative, we kind of took this lower one just to get a ballpark number, and that's how we came up with 70% for our proposed system efficiency. So we did step 1, got our baseline. Step 2, we got our useful energy output. So then step 3 is to convert that useful energy output into a proposed energy usage. And we do that by taking that useful energy output and dividing it by our new efficiency. So that results in about 10,000 gigawatt hours per year in energy usage. And then just for consistency, so we see it in the same way, the climate context for that is about 4.5 million tons of CO2 per year in proposed usage. So last step is compare the two. Again, simplified equation. So our compressed air electricity savings are just going to be baseline minus proposed. These are all numbers that we've seen calculated. So here are the results. So there is a theoretical maximum, and we'll get into the implications with that in a bit, but there's a theoretical maximum of close to 68,000 gigawatt hours per year in energy savings by doing a compressed air phase-out approach as opposed to optimization approach, or 30.2 million tons of CO2 per year. Another way of looking at this is the savings potential is 87% system savings. And to just kind of quantify these numbers a little bit, I used the EPA, CO2 equivalency calculator to kind of put these numbers to other sources. So 67,832 gigawatt hours per year is equivalent to the offset carbon of 10,000 wind turbines running per year, or it's equivalent to the energy, the resulting carbon from 6 million homes energy usage, or 53 billion pounds of coal being burned. And the final metric here is it's equivalent to the atmospheric carbon sequestration of 800 million trees planted with 10-year growth. And then finally, to look at these savings in another light, using the EIA average of the cents per kilowatt hour, it's about 10.5 cents per kilowatt hour as a national average cost. This is equivalent to about $7 billion per year in savings. So that's how we got all the savings. There were a lot of implications in that methodology, and we'll kind of take a look at that in this next section and how zero air compressor manufacturing could look. You've heard of zero energy buildings, but we'll see what zero air compressor manufacturing may look like. So in the paper, we categorized replacement into 4 different tiers that I'll explain a little bit here. To quickly summarize, tier 1 are the simplest. It's going to be 1-for-1 compressed air to motor type replacements. I'll get into that in a sec. And then as we move down to the higher level tiers, these will kind of require more effort and maybe aren't as apples to apples comparison to our calculated methodology. But we'll start in tier 1, and this is a lot of end uses. So tier 1 is easily imagined 1-for-1 retrofits for electric motors. So this is a direct go out to the line, take off your pneumatic end use and replace it with a small motor. Some examples of that include pneumatic tools, materials handling and conveying, air mixing, agitation, etc. So these types of things, it's not too hard to imagine how they could be one-for-one replaced with electric power tools, motor-driven conveyors, etc. And this is a large category. I would love to do a study on maybe what percentage each tier would represent, but just kind of from our experience, this is a large percentage of those end uses, followed by what we would consider the next largest percentage fall into tier 2. And this would be retrofits that are not a direct one-for-one with a motor, but can be a direct one-for-one with other technology, things like blowers, dedicated vacuums, fans, etc. These end uses are low pressure blowing, moving liquid product, cleaning, drying, etc. And again, those replacements are kind of low pressure blowers, fans, vacuum pumps. So while some of these may be direct one-for-one replacements, it's possible that their efficiency is not 70%, which is what we used as kind of the baseline methodology. All right, finally, tiers 3 and 4 are a bit more complicated. So tier 3 is those that would need to be replaced with the system redesign. These are things like diaphragm pumps, bagged house, shakedown, a lot of big vacuum generation type things. These are somewhat of a catch-all category where it's not going to be a one-for-one replacement, and maybe there would need to be a system that would need to be designed in order to replace its compressed air source. And finally, tier 4 is, you got us. We can't swap out 100% of compressed air end uses. So these are the remaining categories which need to be pneumatic, but what we're proposing is it could be a much smaller. If we take out tiers 1, 2, and 3, and all that we're left with is those end uses that require compressed air, then these could be small dedicated systems. Quick examples include if compressed air is required as an input to the product, if there are safety concerns, things like explosion-proof environments, maybe some of these will remain compressed air. Okay. Now we'll get into a case study example to see how we summarized path 1 at the beginning of this presentation, what our current path or the system optimization path could result in. So we're using an audit example from a Midwest automotive glass manufacturer. It had 17 compressors on this site. It was a big system, used about 9.4 gigawatt hours per year in annual electricity usage. And I will say that our effort on this was like a strategic energy management type effort for this audit. What I mean by that is there was ongoing metering and analysis for about 2 years. We identified a multitude of energy efficiency opportunities. And this is kind of, a case example that we would see at a similar energy efficiency optimizing audit. We looked at things like optimizing system pressures, repairing capacity controls, repairing leaks, reducing inappropriate end uses, optimizing compressor sequencing, upgrading the controls. There was a big laundry list, but these were kind of the main savings opportunities. And what we got at the end of this audit is there were about 15.7% of actionable savings. So this is the number that we'll be moving forward with. And just as a separate point to compare to, if we look over here, the DOE has an evaluation of the Compressed Air Challenge training program. This was authored in 2001. What they found was the average system savings from the Compressed Air Challenge was about 7.5% savings. But then this report also mentioned that experts agree that, kind of a theoretical cost-effective savings percentage could be in the range of 30%. So how does our case study compare? Kind of in between these two numbers that came out of the evaluation of the compressed air challenge. So we think that this is a pretty good number, at least give us some ballpark estimates to move from there. So you saw it once before, here it is again. Now you know how we arrived here. So path 1 is what we're on. If we take, this was our baseline calculation, which we got in step 1 of our methodology section, 77,800 gigawatt hours per year are currently being used for US industrial compressed air systems. If our case study example was, we had a similar approach across the nation that resulted in about 15.7% savings, then the total savings across the nation, if we had a similar engineering company go to 100% of all of the industrial compressed air sites, would result in 12,200 gigawatt hours per year in electricity savings. How that compares to a phase out program, I did the math, it's 18%, but in this table you can see we go from the percent savings achieved. So this 100% would mean 100% of our compressed air was swapped out for a 70% efficient motor on down. But the 20% value, that's results in a savings that's close to 100% implementation of our energy efficiency program savings. So this is where we ask the question, which path is more achievable, visiting 100% of industrial air compressors or visiting 20% and phasing them out. So this will be my last slide. When faced with a global time clock to decarbonize, it's critical to reflect on our goals and strategies for compressed air. Compressed air uses a lot of energy. It's extremely inefficient, and a lot of resources go into optimizing compressed air. So we're just kind of asking the question and stating the results of our paper to say that there may be a higher savings potential in phasing out compressed air versus optimizing it. So thank you all for your attention. If you have worked on a similar topic, please do reach out. I would love to share and collaborate on anyone else who might have thought about an air compressor-less manufacturing kind of world. And here's my email if you want to reach out that way or through the conference.
All right, so we're running a little bit short on time for questions, but we will, have that extra time in about 35 minutes or so, where we have the debrief and the breakout sessions starting at 5:15 Eastern time, where we'll try to cover the remaining questions that don't get covered right now. Since we only have 2 minutes left in the session, we can run a little bit over, but I just want to make sure that we're hitting the questions that folks ask. So let me jump right into it. And Chris, I'm going to give you a little time to kind of read through what's going on in the chat. But for Ed and Paul, question, does it make sense to use industrial heat pumps with thermal energy storage? Could it be used with renewables?
I'll start on that. The answer to that, I think, would be yes. The energy cascade of using the waste heat that is available, waste heat can be applied with heat pumps, and storage could be part of that solution. Paul, anything you want to add to that?
Yeah, using storage sometimes makes a lot of sense depending on your application. And where available, using renewable energy always makes sense, whether you have storage or not. Yeah.
Okay, great. Are there issues with compressor operation with very small pitch points?
Paul, I'll let you start with that one.
Compressor, I don't think so. I guess the question is if the lift was so small, it would create a mechanical problem with the compressor. Is that what?
That's right. That's my understanding.
Yeah. Not that I'm aware of, but of course, there you might want to use variable speed on the compressor to deal with that issue. Yep.
Okay, and I'm going to jump to Shashank and Tina for a couple. So tunneling, can this be used for replacing MOSFETs and switching power supplies? How does this technology address standby power versus active power?
So those are both two great questions. I'm going to take them in reverse order. So the leakage current, the off-state current of the TFET is really low, so standby power tends to be very good. The voltage tends to be low, and the dissipation is actually largely in the wiring. So that actually improves the active power as well. So you actually get a benefit on both. That's pretty stiff. That's pretty good. For replacing MOSFETs and switching power supplies, I think there's another technology that's really promising for that called ultra-wide bandgap semiconductors. That being said, TFETs could be really interesting for things like power harvesting. So for really small devices that are at the edge, where you don't want to have, where you have very limited battery power, or if you want to, get energy from heat or something in the environment, this could be very interesting for those kinds of applications. So for like, Internet of Everything, it could be interesting.
Okay, yeah, great. And it looks like maybe Tina and Shashank can't make the later session, so I just want to make sure that their second question also gets answered now. Okay, so what is the energy opportunity associated with DOE electronic appliance efficiency standards using current technology? And then how much could it improve by 2030?
Well, technologically, the answer is it could improve a lot, and we really haven't thought about standards in the R&D office too much, but that is a brilliant suggestion. I did in a former life work on lighting standards, and the one sort of wrinkle is that our standards are on manufacturers because there are a lot fewer manufacturers than sellers, and unfortunately, right now, only 12% of semiconductor manufacturing is done in the U.S. So there'd have to be a little bit of a political agreement, possibly, to get manufacturers overseas to agree to meet these standards. But yay, the U.S. market is pretty desirable. So I think that's a great idea. Shashank, anything to add?
No, that's a great answer.
Thank you.
Great, thanks, guys. So before we jump back to Paul and Ed, I'm going to move on to Chris. Have you looked at ways of overcoming the issue with the size of tools needed for direct motors?
Yeah, so a lot of the questions that I saw in the chat were kind of like, the implementation of, some kind of strategy of phasing out, including this one. I will say that we have worked with a large auto manufacturer, and they were looking at this exact thing, phasing out the compressed air and looking at the cost-benefit analysis of doing that. This specific issue of heavy tools, I have seen kind of pull down on the line, but it might help with that specific issue. But it would be great to go in and look at each facility, see where all of these issues are, kind of document that. And that's also why I mentioned I would love for anyone to reach out to me to kind of help think through this a little bit more.
Sounds good. It looks like John McHugh is pretty interested, so maybe follow up with him. But yeah, just a couple more questions for you, Chris. How durable are motors relative to compressed air motors for situations where there may be stalling in the process?
Yeah, I think that with modern technology, these newer motors are definitely quite durable. Again, though, I don't have a lot of experience in this kind of phase out approach. We were just looking at the numbers to kind of ask the question and see if it would be a viable opportunity. But I do know that, lots of manufacturing facilities do have, blowers on site for that replacement. It's not unheard of to have, electric motors conveying product, those kinds of things. So it is out there, and we have seen it. We just haven't seen it on a large enough scale where, we've the client has completely removed their compressed air to replace with electric motors or other technologies.
Okay, great. I'm going to jump back to a question for Ed and Paul. And the question is, actually, this is interesting because when we had a lot of discussion around non-energy benefits in our first session for this panel. And so this is, I guess, a bit of a follow-up. Are there non-energy benefits that justify industrial heat pumps? And if so, can you, explain a little bit about what you've seen there?
Yes, in addition to the greenhouse gas benefits, there also are heating and cooling opportunities with industrial heat pumps. So you can use them not only for the heat, but you can use them for the cooling part of the cycle. That's particularly interesting for food applications where you may have heating and cooling needs close by. They also can be more controllable and get up to a temperature very quickly and to accurately control at a temperature. So that type of fast response can be a benefit. There also can be improved, somewhat I mentioned there, speed and control, and also flexibility of being able to meet the needs in manufacturing. Paul, anything you want to add to that?
Yeah. So when you are putting an industrial heat pump in, you may be shutting down part of the steam boiler or an entire steam boiler, which that removes the maintenance on that boiler and the associated emissions at the plant. Also, when you capture the heat from the source, heat source, that heat source was normally going to a cooling tower or some type of discharge of waste heat, some type of device. So now that's less cooling that you need to do. And then in many cases, product quality improves because you might be heating or drying that product at a lower, more constant temperature. So product quality might improve. I know that's the case in lumber drying. They really like the nice even heat you get over a time period.
Great, thanks. Yeah, that's really interesting. Okay, and then so jumping back to Chris, I'm sorry, I'm ping-ponging a little bit. Which are the most promising applications for replacement of compressed air?
Yeah. So I guess at the end of the day, in all the manufacturing sites that we've been to, we see end uses that are pneumatic sometimes and electric motor other times. So we do see that there's a wide range. But as far as the most promising, I think just with our tier system that we set up in this paper, anything in that tier 1, anything that's 1 for 1 would be great. Or anything that would be better used with technologies like blowers or small vacuums, kind of following the DOE's compressed air challenge guidelines to instead get a dedicated, alternative technology there instead of using expensive compressed air. But at the end of the day, I think the best thing would be kind of do a system audit, take a look at what all of your end uses are, and maybe tackle the biggest group of things first.
Great. Yeah, thanks. And I think the last question we have for Chris is, if you come across situations where you can eliminate the main compressed air use, but there are several smaller users that are not obvious at first.
Yeah. And I think this also comes back to, we've seen technology in both pneumatic and electric motor. I think that a lot of these end uses that require compressed air at the end use is kind of just a result of, you know, doing industry standards as they are. So everyone's going to have compressed air. So sure, it's okay to require some pneumatic input here. At the end of the day, though, we've seen alternative technologies for probably 95% of these end uses, other than, you know, the product and those things in tier 4 that we talked about. So we think if the industry starts to shift to phasing out compressed air, then a lot of these small uses that require compressed air will start to phase out.
All right. Well, thanks everyone. I think we covered the questions that came up in the chat, but I just want to remind you all that at 5:15 Eastern time, there is a panel debrief where you're welcome to come, you know, chat with the speakers of this panel, or maybe you want to chat up some of the folks in other panels. But yeah, please do come back in about 20 minutes for those debriefs. And thanks, everyone.
Okay.
Take care. Thanks
Thank
for
you,
hanging
everyone.
in.
Thank you.